Right, here's something cool I have just learned. There's something called sorting networks. And the way it works is we imagine that we have some number of inputs, n inputs. Let's say we have 4 to be concrete. What we do is we draw 4 wires. And we imagine that input 1, let's say it is 3, will go on the first wire, input 2 will go to the second wire, input 3 goes here, and so on. Let's say, and we have as input these numbers. Now, and sorting networks are, of course, used to sort things. And the way we do this is we add wires, or like we add comparators to these wires. So what I mean with that is basically we will connect, we can always have the operation that we connect two wires that we have together. So for example, I can take this wire and connect it to this. And what these wires do, what they represent is when we basically what they do is this wire takes as input the two inputs, in this case 3 and 2, and then puts the input that is smaller on the lower wire. And we would like always connect them like to be downwards normally, is I think the default way. And what we can do is we can construct networks with this, like and for inputs I can like draw various of these connections in order to sort them. So for example, if we want to implement bubble sort on this kind of network, we would also, let me make this maybe a bit bigger. They do this. Okay, yes, it's bigger with terrible resolution, but whatever. So we can like implement different sorting algorithms with this kind of thing. And the cool thing about this is, I'm just going to say it now, that if we define the sort with these kinds of networks, we can do nice things in terms of parallelization, running this sort of sorting algorithm on the GPU. So let's implement bubble sort with this kind of structure. We can, like, what is bubble sort? Like, we're gonna like compare the first element to the second, and then we flip them if the based on like which element was smaller, and we do this like throughout the entire array. So that in this case it would just be, correspond to this. Well, and what does this do? Like, it bubbles up. Like, imagine this is the largest element. Or wait, how did I define it? Like, it's kind of equivalent. You could say this moves the largest one down or the smallest one down. Let's say we do ascending sort. That means we want to sort it such that the lowest values are at the bottom, which we say is, well, like at the start of the array, we say the start of the array is here, and the large numbers are here, which is like the end of the array. Okay, let me just do an arrow, very ugly arrow, to say that this is start, this is the end. Okay, so bubble sort, in this case, it would take this first element, let's say it's the largest, and then we swap it with the second one if the first one is larger. And then we do the same for the second and the third element, and then for the third and the fourth. So like, if this is the largest element, then it will end up in the last position, which is exactly what we want if we are sorting for in ascending order. Well, and that of course also works if the largest element is in the second position or in the third, because then we just wouldn't swap here and would swap there, or wouldn't swap for the first two and would swap on the third. And then the next step in bubble sort is to, so like now basically we have, it's the last element is in the correct sorted position. So what we do now is we do the same thing for the second largest thing, so to speak. So we do this, and then we do this for the last thing, and so like So now the largest thing that is still remaining in these 3 wires will go here, and the largest thing in these 2 wires will go here. Okay. Now, of course, this is a really dumb algorithm that's really inefficient. Gonna do a better one in a moment, but let's like think about how this works in this concrete example. So if I'm the 3, then I'm gonna draw with colors. Where does the 3 go? So the 3 would be like, oh, I'm larger than the 2, so we want to go down. Okay, we go down. I am not larger than the 4. So I'm gonna skip this one and go further. Okay, now we need to evaluate the other things. And the thing is, like, the idea is that this dimension here is time. And we want to execute these comparisons from left to right. And the height doesn't matter. So now the 2. We're going to go through here and then we ask, is 2 larger than 4? Well, no, it's not. Okay, now we executed this thing basically for the first 2 values. We evaluated that they skip it. Now we're gonna do the 4. So note that we do not need to reevaluate, like if we flip to this. Normally you wouldn't draw these arrows, I think, by default, but I feel like that's a bit confusing. If you're drawing these lines through here, it's easier to have the arrows because we wouldn't actually, like, we do this flip sort of at the same time, right? These are not 2 independent sort of checks we do for the orange and the green paths. We just do one check on the second and the third input sort of at the same time, or like rather the wire, because we already flipped some inputs. Okay. And also I just noticed here's an error because of course we flipped these. So that's what this thing did. So therefore this goes actually here now. Well, now we see that this will not be flipped. And now we can evaluate this one as like, yes, go here. Okay. Now we evaluate this one. We have like the red as input here. And we have the red, the 3 and the 3 where we already have flipped it. So this is already sorted correctly. So we just go both through. Now we evaluate this one. So we have the 2. Well, and I forgot, we should also, of course, draw the 1. For each gate, kind of, we should evaluate. We need to draw all of the things. It's just that for this gate, well, you need to evaluate all of the things, all of the wires that are involved. So here, if we evaluate this gate, we need to also draw the other input, which of course will be flipped, which is important, such that we can evaluate this gate now, where we see that we get as input the 3 and the 1, which will of course be flipped. The 1 will go up here, and the 3 will go down here. Alright, and there are no more wires here, so we go to the end. For the 4 we also go to the end. Then we have like the 1 and the 2, and yes, the 1 is smaller, so we flip this, and we take the 2 and we go here. Okay, now that means as output we get 1, this is 4, this is 2, this is 3. So we have sorted it correctly with this bubble sort algorithm. Alright. Now, the way that I was walking through this computation is we were just doing the normal thing of going through time and evaluating first this, then this, then this, and this from left to right. But the good thing of representing the sorting algorithm in this way is that we can now we can think of what are the dependencies throughout time that we need. So for example, if we walk through this again, I can start to evaluate this. I'm going to mark it with a circle if this is evaluated. So we have evaluated this. Okay. Now we evaluate this. Okay. And now, well, we would evaluate this. But this one is of course not dependent on this. Like this doesn't change what the output of this would be, of this sorting thing. So we can mark this sort of as this is the first step, this is the second step, and then here we have the third step, but in the same step sort of we can do this also. And you can imagine if you have a network that is really large, like we have like a lot of inputs, and we like if we had a lot of inputs and we just would do bubble sort, then sort of if we are at the end step, we can execute like in the next thing sort of all of the things that are like above like all of the things that are above that, like at least like one wire above it where it doesn't really influence it. So like if you imagine like this was just like basically we can execute this and this, but like if there was a wire on top here, or like many wires, we could execute all of the comparisons here once we are at this point where we have evaluated this way. We can compute all of the things that would be here. If they do not have dependencies. Which of course, if you would just connect them like in the bubble sort, they would actually have dependencies. So, but if you like imagine the thing where like we would have this, and we would have this as wires that were above this, we could execute this, this, and this all at the same time, and it would work. And you want to like, if you do this kind of thing, you want to like construct your network in such a way that this kind of operation is efficient. Like you want to construct in such a way that we can execute as many of the comparisons as possible at the same time. Okay, I've redrawn this in slightly bigger, so it's not as bad in the resolution, but now let's construct as the final thing a network that is actually better than bubble sort. So what we can do is we can take this thing and move it here. So that means like the larger one of the two is now here. Then we can, actually as a quick aside, we can just also write the bubble sort algorithm like this, where we have like these two things are just stacked on top of each other because we can execute them at the same time, which is probably the way that you should write this down normally, because then you can just in a graph structure what things are sort of not dependent upon each other and can be executed in parallel. Okay, here's the example that Wikipedia gives for a better sorting network, which is that we take this and put it here. Then we are gonna take this one and put it here. Then we're gonna take this, put it here, take this, put it here. Notice we do this. This is independent. We can do these at the same time in principle. And then take this and put it here. So the reason this makes sense is that we can think of this as you can think of like, is there a path that a particular sort of value on can take to get to the right position? So for example, we want to make it that the largest value is at the last position, right? So we can think of, is there a path sort of from every wire to the last position, such that like this largest value can flow to the last position, the largest value, no matter where it is. So I mean, if it is here, then it's already in the right position, so that's fine. But what if the largest value, in this case, it's like, I wrote 4 here, so it's in the first step. So how do we get from the first wire to the last one? Well, we can go here, then we can go down via the largest value, so we're gonna compare with this. Then we go here, then we go here. And now we're on the last wire. So that works. What about the second wire? Well, there's just this straight path down here. So if we have largest value here, we're gonna jump there. What about this way? Well, there's this thing here where we just jump down and then we're also there. Now what about the smallest value? We can think of, is there a path for the smallest value to go up? So what if the smallest value is in the lowest part? Well, it can like flow up this thing. I mean, it's gonna compare such that it will take this route, right? And then it's gonna go here, and then it's gonna flow up here. So that works. What about this wire? Well, there's this direct connection here, where we're just gonna jump up there. What about this wire? Well, we have this direct connection here. So okay, that means that if we flow like this, notice we are like at this point in the network now. If we flow like this, then like the smallest value will be in the first wire, the largest value will be in the last wire. Now, that means we basically only need to sort these 2 wires. Well, what do? Well, we're just gonna do this and we're done, because now, well, to sort 2 wires, you just need to connect them like this. Okay, and here's the last thing, just for fun. I constructed using this method I was just describing another network which sorts the thing correctly, though it's probably slightly worse than the example in Wikipedia, because here there's no parallelism at all. So like if you're like, if the smallest value is here, it flows here. If the largest value, the smallest value is here, then it will jump here. If the smallest value is here, it goes here. Largest value again. If it's here, it goes down there. If it's there, it goes down there. If it's here, it already jumped down in the beginning. Well, and then we do the same thing of sorting the things again. Alright, good luck.